Okay, we're going to talk about testing population correlation. And basically what we're doing is testing, is linear regression actually meaningful? Because you can always make a linear regression. You can linearize nonlinear data, right? Everybody remembers doing that. Elise is like, yeah, I did that a bunch on an IA. And
Is that like the log?
yeah, we log the axes.
Yeah.
You do the formula thing like we did yesterday, but with logs. You literally just log everything on the x-axis or log everything on the y-axis, and then in place of y and x, you plug in log y and log x. Um, you just log y if it's exponential, you leave x alone. If it's some sort of power, like x to the power of, you log both axes. So what we're going to do is basically run a hypothesis test that our correlation coefficient, our R, yes, our R, is non-zero. If correlation is zero, or within a certain amount that it could be zero, within sampling error, we say there was no correlation. So in place of R, because R is our calculated one, we are trying to draw conclusions about our population, just like we've always been trying to do. So we're going to use the Greek letter rho. Kind of looks like a P, yeah. It is a little bit,
Yeah.
kind of, not quite, but if you'll notice, I exaggerated the slant on it a little more. Like that's intentionally not, that's not sloppiness, that's intentional. Okay, that kind of makes some sense. So our tests run the same way. You can do a confidence interval on the row. Calculating that by hand's a little messy, but thanks. The graphing calculator can do it all for us. So, which makes this not terribly difficult.
No, this is.
It should be one over there.
This box, I took this home and got it.
Why did you take his box home?
They look the exact same.
As yours?
Unless it's.
Okay. So your Murray's got some data. Or Yuri. Yuri works at a corner store and he has the temperature in Celsius and the number of sodas sold. He wants to see if there's a correlation. So please go ahead and enter this data. Can you guys all pull it up on yours so I can put it into the calculator?
What's that cheese in?
4.18.4. There are 10. So you set up a null hypothesis and an alternative hypothesis. There would be conditions to check on this test, but they're not making you do that for IB. If you're doing actual stats, though, you're putting in a report, you need to check the conditions. Not for this. Not for this one. I don't think they'll make you for any of the others, but I would be, you know what they are. You know, it's SRS. It's possible with a portion that they might ask you on it. So let's run our test. Menu, statistics, stats test. Linear regression t-test. That makes sense, doesn't it? X list that was my temperatures. You name your lists. I can't emphasize this enough. Um, so the alternative is beta and rho is not equal to 0. I think beta is beta is the slope. So we can look at this. We get what should you report on your answer? More than Cognity did, actually. You should report your T. You should report your p-value. You should report degrees of freedom. Probably slope. This is what I'm looking. Yeah. And I believe, usually. And R. I think mine was one, the default. Here, let's take a look at what
Okay.
frequency list is default is one.
See the one, five. Oh, the 1, 0. So I thought it was 0.
No. That's I think that's the not equal list. It's not equal to zero. So yes, T, that's what was missing from a lot of reported answers on your last test. Degrees of freedom should be there. P-value. This one, with having extra things, you should report to me B and R. Okay. Report the calculated ones. So this one is doing it in the traditional stats order, which is y equals a plus bx instead of mx plus b. But that's still the same thing. It's still a line. Your general one is considered alpha plus beta x, where that is the general, essentially variability. That is the true regression line for the whole population. Okay, which do you ever know things for the whole population? No, we estimate them with samples. That makes sense? So we're estimating alpha plus beta x with a plus bx. Yep. Okay, example 2. In an experiment, Matt and Evelyn are simultaneously measuring their reaction times. They both respond to the same input as fast as they can, and the computer records the response times. The table below shows the results of these trials. The times are given in milliseconds. Test at a 5% level whether there's correlation between the two sets of data. So different stimuli checking their response times. And we're seeing if they're correlated and the stimuli matters or if the response time is just kind of random. It doesn't matter what the stimuli is. So go ahead and enter this data. And I am always in favor of just making new ones. If there's a reason, like if you're doing it on the IB test, well, I don't think you can save. I think it shuts off the ability to save. So you can't save, well, you can't share it. You couldn't, if you saved, you could come back to it later. If you're like, I'm not sure on this, but maybe I'll have time to come back to it. So that is kind of a bummer. You probably won't have time, yeah. Okay, so once you've got it, run your test. Cognity has it as a different alternative hypothesis. State whether there is positive. Oh, so we have to look for greater than 0. So they asked if there's a positive. Greater than, yeah. I was like, I was like, I'm just gonna do it and go back and look. So 0.011 at the 5% significance level, yeah, there's a correlation. The input, the reaction time is correlated based on what they're reacting to. And there's only a 1% chance that that was random variation. Now their R value was 0.82. That seems pretty likely that that there is actual legit correlation when the R is that high. Okay. Does that make sense? You're just running the test. You're testing whether whether the R value and the slope are 0. Yeah, like it's pretty much just like the other ones. You can take it further, but they don't. What A and B mean? A is y-intercept, B is slope of the regression line.
No.
No, we know there's a positive correlation because R is positive. That makes sense? As Matt's time goes up, so did Evelyn's, essentially. Okay. Now it's time to talk about type 1 and 2 errors again. First thing we need to get is the meaning. Because if you don't get the meaning, you'll never get the calculations. And if you get the meaning, there's a decent chance you can get a decent amount of the points, even if you cannot get the calculation. So what is the meaning of type 1 error? Well, let's not talk about it in correlation. Let's talk about it in terms of significance tests. Yes, so you conclude HA when in fact it should have been H naught. And what is the calculation always equal to on type 1 error? The alpha level is the probability. So if you did a 5% significance level, your probability of type 1 error is 5%. There's a 5% chance that there was no difference, but your data was just a uncommon data.
Type 1 is when HA is concluded, should have been H.
Yep.
Or is it that H now is concluded, or there isn't enough information?
We concluded HA. We reject H naught and conclude HA, but actually H naught is true. So type 2 error would then, no, you're still writing. Type 2 error as we conclude HA or H naught. We fail to reject H naught, which generally effectively means we conclude H naught. We did the are the chips too salty example before, and we fail to reject means, well, I'm not rejecting H naught. I'm concluding that they're just fine. Okay. So failure to reject often means concluding. So it's concluding H naught when in fact HA was true. And what that looks like is, let's say blue is our actual sample. Red is our sample of what the true distribution is. Okay. So blue is our ideal sample. That's what we're trying to get. Red is what it actually is, but our sample happened to be on the low end of the red, right? And it falls within the acceptance window for H naught on the blue. Even though red's mean is clearly outside of the acceptance window. But I've got all this probability here that falls within that range. That's my type 2 error. My power, do you guys remember what power was? So that's the rest of this. That's the probability that HA is true at a given value. Now we have to assume a new value that we say this is far enough away. This is far enough away to actually matter. This is where you get into that practical significance thing. Okay. Our goal is type 1 error or confidence level of 0.05 and power of 0.8. That's usually the goal on tests. Okay. If you have that, you're feeling pretty good that we're probably going to get good results. So, a light bulb manufacturer states that 2% of its light bulbs are defective. However, its machine was recently repaired, and the manufacturer wants to check whether it has increased the percentage. We talked about this one yesterday, right? This was, I believe, a binomial. Sample of 75 bulbs from the machine is selected at random to test the hypothesis. Find the probability of making a type 1 error when the hypothesis test is carried out at its 5% level. 5%.
What?
Wait. Oh, so this is binomial, correct? And we knew we had 4 or less. So because it's binomial, so with normal and t-tests, it's just the alpha level. Because it's binomial, we have to look at this. We found our critical value before. Let's go review how we did that. So menu, statistics, or probability. Distributions is under both of those. binomial CDF, number of trials 75, probability of success 0.02. I can either look for when it crosses 0.95 or I can go 4 to 75. If I do 4 to 75, that's not 0.05, is it? That does not fall in. So they like to do, it seems like, these type 1 and 2 errors with binomial. And the type 2 error is quite a bit easier with binomial. So 5 is my rejection point. The probability of 5 or more is 0.173. So my type 1 error is only 0.173. Does that make sense? This number? So they'll, this, that's the p-value for 5 or more, or the type 1 error. Yeah, this is just the p-value. If you look at how they did it in the book, they did 0 to 5, or they did 0 to 4, and they did 1 minus that. So I'll run that calculation. I guess I didn't have it in the right spot. Yeah. So they did 0 to 4. I did 5 or more. So what does that tell you? If it's greater than 4, you reject. Now you can't have 4.2 light bulbs. Correct? One minus that is the same. So it's the other side. So on a weekday afternoon, the type 2 error is the harder one. On a weekday afternoons, a northbound train passes a subway station in Bangkok every 10 minutes. We did this one yesterday too. The subway authority has decided to keep the trains that the rate unless the number of people waiting at the train is greater than an average of 50. This was a Poisson, right? The total number of people that will be used to carry out the test at the 5% significant level. The subway authorities carry out the test on the data to determine whether the trains to be considered the critical value calculate the probability of making a type 2 error given the actual mean of people waiting over the course of 1 hour is 335. So yesterday we went and we're looking at the 5%. We need to go with the Poisson until we get to above or below 0.05. That makes sense? Menu, same idea as with this. Poisson CDF.
300.
300 lower bound. I think it was about 328 or 329. Upper bound was, we're just gonna go with 10,000 or 100,000, something large. So I think it was 329. Maybe it was 330. We'll check. I think it was 330. I'm gonna check 329. Somebody check 330.
Mhm.
330 is, 329 is not, so it's 330. So now I've got to look at if the mean is 335, what's the probability of getting below 330? So thinking about these distributions, I have one here centered at 300, and my rejection interval is 330. My type 2 error, this is 335. I'm trying to find the probability of being in here. Does that make sense? So these drawings can really help. A little quick sketch. So I'll do my Poisson CDF. I should just hit buttons. Oh, no, I need to do distributions, not tests. My new mean value is 335. I'm actually looking for the 0 to 330 range. Well, no, 330 I'll still reject, so I got to do 329. Does that make sense? Yeah. I can't have a partial person. My type 2 error is 38.5%. I believe that's correct. So we found it was 330 was our rejection point, which in this case, I'm looking at 329 or less, 38.5. You just got to remember how to do this. There'll be some practice problems. That's it. You guys have some time to actually get going on 4.18 right now.